Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On, and in this tutorial video, I'll go through this November 2015. This is a paper 1-1 for this November 2015 Cambridge International A-Level curriculum, which is pretty much similar to any A-Level curriculum, 16 to 18 years old, taken by students all around the world. In this first question, we have some successive ionization energy. So we know that ionization energy means that we are progressively removing one electrons from the atom and the resulting ions. So from the first, the second, the third, we are looking at where the biggest jump is. And hopefully you can see that the biggest jump, there is a sudden increase, much higher increase in ionization energy between the fifth and the sixth ionization energy. What does this tells you? This basically tells you that the sixth electron must be removed or must be ionized from an inner shell. So if you remove it from an inner shell, that will be closer to the nucleus. If you are closer to the nucleus, you are going to be less shielded. If you are less shielded and closer to the nucleus, much more difficult to remove. So if the sixth one is much more difficult to remove, that means the fifth one is the very last one from the outer shell. So it means altogether, you must have 5 valence electron. Valence in this case refer to outermost shell electrons. If the sixth one is very difficult to remove because of the reason I just outlined, that means this element X must only have 5 outer shell electrons, 5 valence electrons, and this corresponds to a group 5 or a group 15 element, which means for a group 5 or group 15 element, what is going to be the formula of the chloride of group 15? We can be imagining things like NCl3, but we don't have NCl5. That is because nitrogen is a second period element. So in the second period, you only fill up to the second shell. So that means you can only accommodate 8 electrons in the second shell maximum. However, if you have phosphorus, which is 1s2, 2s2, 2p6, 3s2, 3p3, for a group 5 element or group 15 element. So because you're in the third period, you can accommodate up to 18 electrons because from the third period onward, you have these d orbitals that can accommodate a further 10 electrons. This is called the expansion of the octet. Octet because 8 electrons within the s and the p, but you also have the 10 extra electron space from the 3d. The third element, the third period elements onwards can expand their octet to have more than 8 electrons in the outer shell. So you could also have PCl3. You could also have PCl5. Things like SF6 is also possible, but there's sulfur. So looking at the formula of the possible chloride, we're looking at C as the only possible answer in this first question. Question number 2, we're looking at the highest yield of ammonia. Ammonia is your product on the right-hand side. You want the equilibrium yield to be the highest. So Haber process is a well-known process. You know that the forward reaction is exothermic. So we're looking at Lee-Chatelier principle. Lee-Chatelier principle says that for a system in equilibrium, if you introduce a change to a system equilibrium, the equilibrium will try to oppose the change so that it will return back to equilibrium. So first of all, if the forward reaction is exothermic, if I decrease temperature, if I increase temperature, so that means what would the system try to do? The equilibrium tries to decrease temperature. What does this system do? The forward reaction is exothermic, it releases heat. So therefore, the system, meaning the reactions, will release less heat because you want to try and decrease temperature. So you will release less heat because all it knows to do is to release heat. So to decrease temperature, you just release less heat. And when you release less heat, as you're going from left to right, you release heat. To release less heat, you will favor more to the left-hand side. Therefore, equilibrium shift to the left, or they will favor the left-hand side, which means your equilibrium yield of ammonia, which is on the right-hand side, would decrease as the equilibrium shift to the left. What do we want? We want the highest yield of ammonia. We want to favor to the right-hand side. Therefore, we have to go to the opposite. So we don't want high temperature. We want low temperature. Okay. In terms of catalyst, so whether catalyst is absent or present, they will not affect the yield because they only affect the rate. and not the yield. Okay, they never ever affect the yield because the catalyst is never used up in the reaction. In terms of pressure, you look at the gaseous component, you have 4 moles of gas on the left. If you have 4 moles of gases on the left hand side, and this is versus 2 moles of gases on the right hand side. So as you imagined, if you increase pressure, so this side, the right hand side has 2 mole of gas, there will be lesser pressure. If you increase pressure, so as pressure increases, equilibrium tries to decrease the pressure. So what will happen is the equilibrium will try to shift to the side with the lesser gaseous molecule. I beg your pardon, not decrease temperature, but decrease pressure. So that means the equilibrium will try to shift to the right hand side, to the side with the lesser number of gaseous molecule in order to oppose the change. In doing so, it will produce more ammonia, giving you a higher yield of ammonia. So high pressure is what you want and not low pressure. As a result of it, just by looking at catalyst present or absent, it's not going to affect the yield. Whether the catalyst is absent or present, it will not affect the yield. So what we're looking at really is pressure and temperature. So that's the only one that will give you the combination that will give you the highest yield of ammonia. And people might thought that you need the catalyst to give you the highest yield. They might have crossed out A and B and end up with the wrong answer. So be very careful there. Question number 3, so you do need a data booklet for this question. So this compound here S2O7, which is basically oleum, if I'm not mistaken, and you hydrolyze it in water to produce you sulfuric acid and also oxygen molecule as the only product. As with any mole calculations kind of questions, you always have to balance the equations. So you've got 2 sulfur on the left hand side. So the easiest thing is to balance this with 2 because you want 2 sulfur on the right hand side as well. The next thing is looking at the hydrogens. You have 4 hydrogen atoms, so you need 2 of that water to give you 4 hydrogen atoms. Last but not least, total up the number of oxygen, 7 oxygen atoms. 2 times 1 is 2 oxygen atoms. 7 plus 2 is 9 oxygen atoms. Here you have 2 times 4, which is 8 oxygen atoms. 9 oxygen atoms on the left, you need 9 oxygen atoms on the right. You already have 8, you just need 1 more oxygen atom. Just 1 more oxygen atom. But you are given a molecule because that is how it exists as. We use a half because a half multiplied by 2 give you 1 oxygen atom. After we obtain the balance equation, the next thing is really looking at the reacting ratio. So what we have here, this is the mass. This is the mass of S2O7. If we have the reacting mass, we really should be thinking about the MR. So straight onto the data booklet, the periodic table. 32.1 is the AR of sulfur, multiplied by 2 plus 16.0 times 7, I get 176.2. Mass over MR will give me the mole of S2O7. What else do they want? They want the volume of oxygen. They want it measured at room temperature and pressure. From your data booklet, your periodic table shows you 24 dm cube is the volume for 1 mole of any gas at RTP. But all the questions options here, they are in cm cube. So we'll be looking to use 24,000 cm cube per mole instead of the 24 dm cube per mole because 1 dm cube is 1000 cm cube. So if you have watched my other tutorial video, you will know I'm a big fan of putting everything in one go. So I will set up my mole ratio like that. The mole of the oxygen, on the balance equation, is a half on top, and I got 1 mole. 1 mole of these S2O7 produce half mole of O2 as I have labeled them. On the far right, I will put in the actual amount that reacted. The O2 is a volume of gas, so the volume of O2 is what I want. And I'll use division by 24,000 because that will be the volume of oxygen in cm cube divided by cm cube per mole. This is the actual mole of O2 that get produced from this mole of S2O7, which given the reacting mass, it will be mass over MR. So that will be divided by 176.2. So what you could do now is you're just doing some math, and you could hopefully see that that will come down to a half multiplied by 0.352 divided by 176.2, and you could bring up to 24,000, and this will be equal to the volume of the O2 when you press your calculator correctly. So I get the volume of O2 being 23.97. This will be in cm cube, so give or take 24 cm cube. That's the closest option there, option B. All right. On to the next question, we have nitrogen molecule and also carbon monoxide. Both of them have the same MR, where this one is 12.0 plus 16.0, whereas this one is 14.0 plus 14.0 there. Both of them will give you 28. But the boiling point of N2 is 77 Kelvin. The boiling point of CO is 82 Kelvin. So this one has a stronger intermolecular forces between the molecule. And what is the reason for that? Well, if we think about this, both of them are simple covalent molecule. And when you have simple covalent molecule, so that means you have simple covalent structure. When you do melting or when you do boiling, you are never going to break the covalent bond. Instead, what you break is you break the weak intermolecular forces between the molecule. When you have N and N triple bond and CO triple bond, in fact, one of these is a dative covalent bond from the oxygen to the carbon, so that you still have a lone pair on the carbon and you still have a lone pair on the oxygen. Whereas for the nitrogen, well, they look exactly alike, except that this one has a dative covalent bond. This one is non-polar because both the atoms have the equal electronegativity, whereas CO molecule is polar. You have two atoms that are of different electronegativity. If you are a polar bond, in this case, you only have you only have the bond between the two atoms. If the bond is polar, you're going to end up with polar molecule because your whole molecule consisted of that bond between the two atoms. If you have polar molecule, you will have permanent dipole. Permanent dipole is going to be stronger than just van der Waals forces between the nitrogen molecules, and that is why you require a lot more energy to break the permanent dipole compared to only just the van der Waals between the N2 molecule, and therefore option A is the reason why it takes slightly more energy to break the permanent dipole between the CO versus only van der Waals between the N2 molecule there. Question 5, this is about SiO2 chemistry in O level, GCSE level or IGCSE level. You will learn this as silicon 4 oxide. Sometimes they call it silicon dioxide. So basically it's a component of sand, so sometimes they call it sand as well. But typically these are not the desert kind of sand, it's more like the white color kind of sand. How does the structure look like? The silicon is actually tetrahedral. So around the silicon is bonded to 4 oxygen, 4 single sigma covalent bonds. And around the oxygen will form 2 covalent bonds around each oxygen. So each oxygen is bonded to 2 silicons. And it's a band geometry around each oxygen where you have 104.5 because you still have 2 lone pair around the oxygen, but around the silicon, the bond angle is a tetrahedral geometry 109.5 degree there. So all of these are definitely a covalent bond, definitely not ionic. This is a part of this topic called giant covalent structure. So they call it giant covalent molecule. I'm not too confident, not really about confidence, but really I'm not too comfortable calling it a molecule, but I do know the giant molecular structure, giant covalent structure is what you will be accepted in the curriculum. Okay, so each silicon is bonded to 4 oxygen atoms, so 4 and 4. Each oxygen is bonded to 2 silicon atoms, and all of them are covalent bonds, so only C is correct. Obviously, you're expected to be able to sketch this out very, very easily, okay? So in this next question, we have solid sulfur. We are told that it's made out of this molecule, S8, and we have this bonding in sulfur dioxide, which actually is this slightly bent molecule because it consists of 1 bond pair and 2 bond pair and 1 lone pair, such that your bond pair lone pair repels more than bond pair. Based on your valence shell electron pair repulsion theory, this is actually a special kind of band. It's a band with 120 degree instead of the 104.5, as you will find in water as a result of having 2 lone pair in water molecule. Okay, so what this question is about really is you want to find the S or bond enthalpy, so basically the bond energy. So if I let the S double bond O bond enthalpy be X, in one molecule of this we have 2 sets of the sulfur oxygen double bond. We are told that this is the combustion of S8. If we write S8 solid, and then when that combusts, that's gonna combust in excess oxygen, and that gives us SO2 gas. Balancing equation is very important. So I have 8 SO2 because I have 8 sulfur atoms there. So 8 times 2 is 16 oxygen atoms. I need 16 oxygen atoms. That means 8 oxygen molecule. That is going to be the combustion. So that is minus 2376. That is combusting 1 mole of S8 according to the information given. The other thing is, this is atomization. It's not really atomization because you're breaking 1 mole of S8 and you're going to form 8 mole of sulfur gaseous atom. So that, based on the information, that alone is 2232 kilojoule per mole, but that is forming 8 mole of this gaseous atom. So this is actually 8 times the atomization of sulfur based on the definition. In terms of the atomization of oxygen, it's very similar, it's not equal, very similar to this bond enthalpy, but here we are breaking 8 mole of these gaseous molecule of oxygen. It's the same as breaking 8 mole of these bond enthalpy of oxygen. So that is 496 multiplied by 8 because I'm breaking 8 mole of that oxygen molecule. On the other hand, I'm going to break up all the covalent bond in the SO2 molecule. In one molecule, I have 2 of these covalent bonds. So 2x for one molecule. I have 8 of that molecule. So altogether, I have 8 times 2x because x is the bond enthalpy for one of these SO double bond. I have 2 of them in one molecule. I have 8 molecules. So I have 16x altogether. All of these will be broken down into the oxygen atom, and there will be 16 of that oxygen gaseous atom. So Hess law says that the enthalpy change of a reaction does not depend on which path you take. So this is like a direct path, this is like indirect path, as long as you start from the same reactant and end up the same product. So based on the Hess cycle or Hess law there, minus 2376 equal to 2232 plus 8 times 496, and then I'm going the opposite way from this direction, so I'm going to have minus 8 times 2x, so that is minus 8 times 2x, that is minus 16x. So I'm going to move my minus 16x to the other side and move this minus 2376 to the right hand side. I'm going to end up with 16x on the left hand side. 2232 plus 8 times 496, 2232 plus 8 times 496, I get 6200 plus 2376. So x is going to be 6200 plus 2376. There's 8576 divided by 16, and I get my answer is 536 kilojoule per mole, and that is equivalent to option number D there. Okay, so hopefully that makes sense to you. Question 7, I've used a bit of space there for the previous question, so perhaps I wonder if I can just move my working somewhere. I cannot find enough space anywhere at all. Yep, I cannot find enough space anywhere at all, so probably I just leave it there as it is for question 6. Question 7, so we have an experiment. We need to burn 1.45 gram of propanol in order to heat up 100 gram of water. Initial temperature is 20 degrees Celsius, final temperature is 78.0 degrees Celsius. What is the experimental value for this enthalpy change of combustion that you can calculate from these results? So we have propanol, and we were told about that this is however much mole of propanol, so we don't have to worry about mass over mR to work out the mole anymore. But then we know the water there is the temperature of the solution, and we have heat capacity of the solution, which is just water. So that is from your from your data booklet is 4.18 joule per Kelvin per cm cube, but it could also be joule per Kelvin per gram. It could also be joule per degree Celsius per cm cube. It could also be joule per degree Celsius per Kelvin. All of that is because 1 gram per cm cube, that is the density of water. Okay, so we are heating up the water, and what actually happened then is your heat energy is delta T time mass time the heat capacity of water. We have 100 gram of water multiplied by 4.18 for the heat capacity of water, and then I got to multiply by the change in temperature, which is going to be 78.0 minus 20.0. That is the actual change in temperature there. Let me just move this up some way so that I will have enough space to write there. So what do we have? 100 times 4.18 times 78 minus 20 in a bracket. So I get 244 joule. However, if you look at the options, they are all in kilojoule per mole. So enthalpy change is to do with heat energy per mole. It's to do with stoichiometry. So it's 24244. This is joule. So I got to multiply by 10 to the minus 3 to convert it to kilojoule. That's divide by 1,000. And this thing raised the temperature of the water. It gets hotter. So I can say that this is going to be an exothermic reaction. So that's because it gives out the heat energy, and therefore the water increase in temperature is an exothermic. It's got a negative sign, as all of these sign has shown you. Sign, value, and unit, very, very important in the topic of stoichiometry, as well as, sorry, not stoichiometry, in the topic of physical chemistry, such as these energetics. So 24244 divided by 1,000 and then divided by 0.025. Actually, I get minus 969.76. This will be kilojoule per mole. So the closest this one is to the answer is minus 970 kilojoule per mole to 3 significant figure. As you will see, that will be option number B there. Question 8, this thing has been removed from the electrochemistry syllabus. So it used to be in the AS electrochemistry, but I think this has been taken out from the current syllabus in the AS electrochemistry. So you don't really learn it anymore. But back then you would have to learn it as the concentrated NaCl, as you would know from O-level, GCSE level, or IGCSE level chemistry, where you have Na plus, Cl minus, H plus and OH minus, but because as a result of the concentration, it's going to favor the Cl minus being discharged, and that will give you Cl2, that will give you H2. You're left with just the Na plus and the OH minus, such that the pH 7 that you started out from, that is your salt solution, that will slowly become more and more alkaline, giving you NaOH as well. In terms of the balance equations, the NaCl plus the H2O will give you NaOH, that will give you H2, that will give you Cl2 as well. The H2 is produced at the cathode, the Cl2 is produced at the anode, and then this is just the resulting pH of the solution that remains. That's the alkaline solution. Of course, we have to balance our equation, so there is 2 of that, and what do I have? Then I have 2 of that, and I think that equation is balanced. I think, nope, the equation is not balanced, so I have 2 hydrogen, 4 hydrogen, 2 oxygen there, 2 sodium there, 2 chlorine. The equation is balanced. Okay, in terms of the anode and the cathode, we don't use steel, which contain iron, because that will react with the chlorine to give you iron 3 chloride or iron 2 chloride. So we never use steel for the anode. We use titanium for the anode, but we do actually use steel for the cathode. Okay. Question number 9, which is actually in the current A-level syllabus, we have a skeletal formula of this hexamine. We're going to learn to read skeletal formula. The most important thing in the skeletal formula is carbon form 4 bonds. You don't show the hydrogen bonded to the carbon. They want you to get the empirical formula, which is defined as the simplest whole number ratio of atoms. As stated in the syllabus, candidates should be able to state empirical formula is the simplest whole number ratio of atoms. So what we have there is we have 2 hydrogens. Because carbon form 4 bonds, there is 1 bond, there is 2 bond. So that means the thing that it doesn't show, carbon form 4 bond, 1, 2. So there's still 2 more hydrogen there. The same thing for this bridgehead there. So these are CH2, CH2, CH2. The same thing can be said for this thing here, as well as this thing here. So what I have is, I have 6 of these CH2. Those are the bridgehead positions, the junction there. And I have 1, 2, 3, and 4. I have 4 nitrogens. So altogether, this is my molecular formula, C6, H12, and 4. This is called molecular formula. So empirical formula just now was the simplest whole number ratio of atoms, whereas molecular formula is the actual number of atoms in one single molecule. A lot of students always forget that is the actual number of atoms. They get that, but they forget the second bit in the definition. This is in one single molecule. In one single molecule, you have this much actual number of atoms. So if you simplify that, you divide by 2 throughout, you're going to get C3, H6, and 2. That is going to be the simplest whole number ratio of atoms. There's option number B there. Question number 10. This one looks like an equilibrium constant kind of question. Oh yeah, this one is actually pretty easy because they already told you that at equilibrium, what is the mole? The mole at equilibrium, they told you they have 7.2 mole of N2. This is already at equilibrium according to the question. All right, so you have 12.0 mole of H2 in this equilibrium mixture. You don't know what is the concentration of ammonia, but be careful. This question is asking you on concentration, whereas this information given was mole. These are mole, they are not concentration. Concentration is going to be the number of mole divided by dm cubed. As you could see from the unit, they never lie to you. They deliberately show you mole per dm cubed for concentration. These are mole. So your job really is find out what is going to be the information there. Let's see. So if you have concentration at equilibrium, what are we going to get? We're going to get 7.2 mole divided by 6.0 because this is the total volume. Mole divided by dm cubed. 7.2 divided by 6.0. I get 1.2 mole per dm cubed for the concentration of N2 at equilibrium. 12.0 divided by 6.0. I get 2.0 mole per dm cubed. The calculator will not show me 2.0, but we need to be appropriate and sensible based on the information given. Now I want to find the concentration of the NH3 at equilibrium. Well, I look at the expression. The Kc is 6.0 times 10 to the minus 2. So that is the thing there. This is equal to the concentration of the NH3 square divided by the concentration of N2 to the power of 1 because there is only 1 in front of the equation. There is 2 in front of the NH3 in the equation. And now at the bottom, I also have the concentration of H2 to the power of 3 because I have 3 in front of the H2 in the equation. So what I could say then is I want the concentration of NH3. So that is going to be the x squared, I guess, divided by 1.2 mole per dm cubed, divided by 2.0 to the power of 3, 6.0 times 10 to the minus 2. Of course, then you're going to bring up the number, as you would know from doing simple mathematics. So be very careful, use bracket, and do not get confused. We still have the cube, so x is going to be the square root of something. So I'm going to put in 6 times 10 to the minus 2 times 1.2 times 2.0 to the power of 3. I get 0.576. So I need to square root 0.576 because this is square equal to 0.576. So I'm going to get a square root, which when I square root it, I'm going to get 0.7589. And looking at the option here, it seems like 0.76 is going to be the appropriate answer there for the concentration of the NH3 at equilibrium. Question 11, this is about Haber process, just like the earlier questions. Previously, they did mention that it's exothermic in the forward reactions. Here, you don't want the yield, you want the rate of the forward reaction. Rate is to do with how fast, equilibrium yield is to do with how much. Okay. Now, option A, if you add argon to the mixture, so that means this will increase the you keep the total volume of gas constant, but you have more argon. If you have more argon, keeping the total volume constant. If you have more argon, oh wait, hang on. I'm not thinking about equilibrium, right? I'm talking about rate. So adding argon in there does not make your rate go faster because this will decrease the amount of successful collision between your reacting particle. So it's not going to increase your rate of reaction because you introduce more argon. That means there is lesser because total volume remain constant. So there's lesser of reacting molecules, the thing that actually reacts. So if you have lesser of reacting molecules, less collision frequency, the rate will slowly decrease. So that's not going to increase the rate. Decreasing temperature, this is not how much. Be very careful. We are talking about how fast. So we know that in terms of temperature, it does two things. One thing is to do with the energy distribution. That is to do with the Boltzmann distribution. So at the lower temperature, you will shift the Boltzmann distribution to the left-hand side. The number of molecules with energy E on the y-axis. This is the energy E on the x-axis. If that is the case, that means when I increase temperature, I will shift to the right. But when I go to lower temperature, this is when temperature decreases, I would decrease the proportion of effective collisions because I will have lesser molecules that have enough energy to react. At the same time, I also talk about kinetic energy decreasing, and then collision frequency will also decrease. Both of these factors result in decreasing temperature, decreasing the rate of forward reaction. So that is wrong. Now between C and D, if I increase pressure, so that's the idea, increase pressure, these are all gaseous reactants. If I increase pressure, pressure is force over area. So when I increase pressure, I squeeze the reacting particles closer together. They will collide more frequently, and this will ultimately result in a faster rate of reaction. The last one, removing ammonia, is something that you would do in the actual industry scale. In order to decrease the concentration of ammonia, then this equilibrium will shift to the right hand side to try and increase the concentration of ammonia, to try and increase equilibrium yield, but it doesn't change the rate of the forward reaction. Okay.